So last time I was talking about how the p-local homotopy type of classifying spaces of finite groups was somehow determined by the isomorphism type of these triples that we define. This triple where you have a finite group, a fusion system, and a central linking system. So let me remind you of the theorem that we were talking about. So theorem. BG P completed at P is homotopy equivalent to BG prime completed at P if and only if the triples these triples were isomorphic. And here, remember that an isomorphism meant an isomorphism of these two P groups, which are the P silos of G and G prime, respectively, and that these isomorphisms induce isomorphism of categories of the fusion system and the centric linking systems. Okay, so that was the statement. And at the end, I was trying to explain why this was true. So on the one hand, going that way was easy, because we proved that the geometric realization of these spaces are precisely homotopy equivalent to this. So if these two categories are isomorphic, then the geometric realization are homotopy equivalent. Now, to go back, to go in this direction, what I was explaining is that actually these fusion systems and centric linking systems have an alternative description in terms of the classifying spaces. So I was saying that, so idea that this category has an alternative description, an equivalent description, as follows. Again, the objects are the P-centric subgroups of S, but the morphisms could be given in terms of these commutative diagrams. So the morphisms from Q to R were group homomorphisms such that when you look at the diagram, and when we take the classifying map, and then we look at the inclusion into BG be completed, then this commutes up to homotopy. Okay? So in particular, if we have a homotopy equivalence here, that's going to induce an equivalence of the two fusion systems. Okay? And we also have an similar description for LS for the centric linking system. So again, the objects are the same. The objects are P-centric subgroups. But now the morphisms are given by a bit more information than that. So now the morphisms are pairs F phi, where F is again a group homomorphism such that the same thing happens. So this is BF. But since we have a homotopy equivalence here, this phi is actually just that, a homotopy that realizes this homotopy equivalence. So phi, well, this class of phi is a homotopy class of homotopies let me give names to that. So let's say I call this IQ and I call that IR from IQ to IR composed with BF. And sorry, can you repeat?
So it's the same category, but now we're going to type on exactly what
Yes.
it makes it can do.
Yeah, yeah. So I'm getting more information. I mean, not only that it's homotopic, but how it is homotopic. Yeah. So, and if you remember that we had a projection from the central linking system to the fusion system, makes sense that the central linking system has more information. And in fact, the projection here will be just for getting the homotopy. So I guess now it makes a bit more sense. I mean, there are some details here that I haven't talked about. I mean, when I said here that we have an isomorphism, the isomorphism has to be induced by a map from S to S prime, right? But one can check that this actually agrees with that. That's a bit more technical. Now, anyway, if you remember back at the beginning, a few days ago, all this came about from this Martino-Peretti conjecture. And the Martino-Peretti conjecture didn't have this third category. It only had the first two, right? So we have proved now one of the two implications of the Martino-Peretti conjecture. I mean, we have proved that, well, we have proof. Gives you the sketch of the proof. We have proved that if these two are homotopy equivalent, well, then we have an isomorphism of the pairs. Without looking at the third, in particular, we have. But how do we go back? If we have an isomorphism of S into S prime that induces an isomorphism of the fusion systems, how do we know that that's going to induce also an isomorphism on the central linking system? And this is actually the hard part of the conjecture that Oliver proved. Remember I told you that the Martino-Peretti conjecture is now a theorem by Bob Oliver. So now what is the idea of the proof? Well, the idea now is that what happens if you have an isomorphism of these two things? Yeah? What you now want is to lift this isomorphism to an isomorphism of the central linking systems. And then you will prove the theory. Yeah? Does that make sense? Yeah? Well, what this requires, so we need to show that an isomorphism, can I write that, of fusion systems I guess I'm missing here some things, leads to an isomorphism of the central linking systems. Yeah. And now here one uses obstruction theory. And obstruction, see. One could use the centric on the non-centric. It's really equivalent since the categories are generated by centric subgroup. But I guess the original statement was without centric, but it doesn't really matter who's centric or not. Yeah. So now, like I was saying, one uses obstruction theory, and one proves that one isomorphism leads to an isomorphism of central linking system if and only if an element in the limit over the orbit category of the functor Z vanishes. Okay? I guess I haven't talked about this orbit category except when Paul asked me about it. But the orbit category is just the same thing. It's a quotient, so in the orbit category, the objects, again, are subgroups of S, and the morphisms from P to Q are, well, the morphisms in the fusion system, but quotient by Q, by conjugation by Q. Or in other words, you can also see this as GQ fixed points by the action of P, to make it more like Mike was talking about them. And this C is just the functor that to an object gives its center. Right? So anyway, one can show that an isomorphism leads to an isomorphism of central linking system if and only if certain element that depends on this vanishes. So what Oliver did to prove this theorem was to prove that actually all higher limits vanish. Yeah, so these are the derived functors of lim. So if you haven't seen what these lim ends means, I mean, probably seeing the derived functors of Hom functors or tensor, right? You know that they have derived functors. So for lim, for limits, for inverse limits, they are also not exact. So they also have derived functors, and these will be the derived ones. So like I was saying, Oliver showed that the limit, all the inverse limits vanish for all n bigger or equal than 2 and all finite groups G. But now this proof is not easy at all. I mean, it's a big article. It's a bit technical, and it uses a lot of things about group theory. It's sort of a reduction first from general groups to simple groups, and then we have the classification of finite simple groups. Then we use the classification sort of check that is true for all of them. So it's kind of long. And it's
greater than 2 or
greater or equal than 2 for all of them. Yeah, I mean, we only needed this one, but he actually proved for all. So it uses the classification of finite simple groups. I mean, definitely not a simple thing to do, and of course we would like to see something simpler, that it wouldn't use the classification. But that's just, at the moment, that's dreaming. In fact, one of the reasons that people studied also people started with the p-local with homotopical group theory was also trying to understand or trying to give a better explanation for the classification of finite simple groups. So they thought that maybe putting some topology, maybe some of the results can be simplified, some of the projects. But it turns out that that hasn't got to a good stage, because as you can see, even for some of these results, we are still using the classification. So not really what people expected at the beginning. So anyway, enough about the Martino-Pridy conjecture. So now I would like to go to the abstraction of fusion systems. So far we've been talking about something very concrete, which are finite groups, and how to build these categories out of them. But I would like to talk just briefly about an abstraction which are called p-local finite groups. Okay, so what are p-local finite groups? It's an abstraction of what we've done, of these triples. And they are due to Brotto, Levy, and Oliver. So the idea is, we know that the p-local classifying spaces of finite groups behave in this way, that the homotopy type is determined by these triples. Now we would like to find other spaces that behave in the same way, but they are not classifying spaces of groups. Okay, so that's the idea. So this abstraction starts from the fusion system. So how do we abstract that definition? Well, let's imagine that we have a group, but now we don't have the group. We only have the p-silo. So let S be a finite p group. Then a fusion and saturated fusion system F over S is a category whose objects are again the subgroups of S. So we're starting just as if we had a group. But now with the morphisms, we have a few conditions that they have to hold. So let us denote the morphisms in this way, as a home set. So we are imagining that these morphisms are G conjugations by a group G that doesn't really exist, okay? But if we have all the conjugations by the group G, in particular, we will have all the conjugations by the silo subgroup. So we need to contain these ones. They should be included in there. Does that make sense? Yep. Also, every conjugation is an injective homomorphism. So we want this to be injective, to be contained in the monomorphisms from Q to R. So we want that our morphisms satisfy that. We also want morphisms to satisfy that the same property that every conjugation is an isomorphism to its image and then an inclusion. So every morphism is the composition of an isomorphism followed by an inclusion. Okay? And I'm not done yet. And here there are other two technical conditions. Now I could write them, but you're not going to get anything new out of seeing them from the first time. So I'm just going to skip it, and let me just say that these technical conditions make S look sort of like a silo subgroup of this group that doesn't exist. So they are kind of maximality conditions. Okay, so you can see how this comes from the other definition. Now, do these saturated fusion systems satisfy the same properties as the other one? Well, for a start, we have that they also satisfy this Alperian fusion system, that the morphisms are generated by morphisms of centric subgroups. But of course, here we have to define first what a centric subgroup is. So, definition, a subgroup QS is F-centric, centric with respect to this fusion system, if the centralizer in S of P is equal to the center of P for all P isomorphic to Q. In F. Now this seems quite different from the p-centric definition, but of course in the p-centric definition we had G. Now we don't have G, we cannot use it. So we need to find an equivalent way of stating that condition without using G, and that turns out to be this one. Because we have to check that when we have a group G, this is equivalent to the other condition. And like I was saying, with this definition, we have an analog of Alperin's fusion system. Alperin's fusion theorem, sorry. Morphisms in F are generated by automorphisms of F-centric subgroups and inclusions. So just like in the case of a finite group. And again, I have to say here, for those who have seen this before, this is not the full statement of Alperin's fusion system. This is just a corollary of the fusion theorem. But this is enough for what we're doing. And now, if you remember how we arrived to the central linking system, it was a whole process, right? Talking about phantoms, homotopical limits. But at the end, what we got essentially was that the central linking system is sort of a lift of the fusion system, right? Kind of a quotient by the center. So here, the definition is going to be the same thing. So definition, a centric linking system L associated to F is a category whose objects are now the F-centric subgroups Now, this category must come with a functor from the linking system to the full subcategory of F whose objects are centric subgroups, yeah? And such that this functor is the identity on objects, which is the identity on objects. I mean, we are just mimicking what happened in the other case. So this happened. But on morphisms, and on morphisms, we have the morphisms from Q to R, quotient by the center of Q, is isomorphic to home from Q to R. Yeah, this is something that happened on Friday, right? So again, we want the same thing to happen now. And again, here I'm not telling the full story. There are still two more technical conditions. So I'm going to just say, I'm not going to state them. There's two technical conditions. They're just conditions of compatibility with the same conditions that we put for the fusion system. Yes?
When you quote it by ZFQ,
Uh-huh.
what does that mean?
Right. So what it means, I mean, this is something that is hidden here too. But in this technical condition, it says that we have an action of C of Q on Q. Sorry, on the set of morphisms. And the quotient by this action is isomorphic to that through this pi. I mean, I'm hiding a lot of information. I really don't want to spend a lot of time on this, just giving you the idea of how they work. Because they are really technical at the beginning, but. Okay, so this is all the information that we need to define the analogous. So now, definition, a p-local finite group is a triple SFL, where S is a finite P group, F is a saturated fusion system, and L is a central linking system associated to F. So that's the definition, okay? And to this triple, we associate a classifying space. This classifying space is the geometric realization of L, P completed. Okay, does it make sense? Okay.
Does P enter into anything until you?
Here, finite P group.
Oh.
Yeah, so we have the P silo. Yes.
I just wondering, like, in what sense it's like saturated? Should it make sense?
Oh, well, you remember somebody, the first day somebody asked me if it would make sense to talk about FSG when S is not the P silo, right? So it makes sense to do the same definition. But in this case, the two technical conditions don't hold, right? So saturated means that really S works just as a P silo. But one could also make the definition of a general fusion system, which is sort of the generalization of this when S is not the P silo. But yeah. Now, why they use the term saturated? I think it's random. I'm not sure about that. Okay. So now, yes.
Can you give an example of this?
I wish I could give an example, because this is always the question. Now, of course, when one does a definition like that, one expects that one gets more examples than the one that we already have, right? And there are.
Okay.
Unfortunately, they are hard to construct. I'm going to mention something about them. I'm not going to construct them, but hopefully that's enough. But before that, let me just talk a couple more things, and I'll talk about what are called the exotic examples. Okay, so first let me tell you that this definition is sort of the correct one, because we still get the same theorem that we had at the beginning or last time. Theorem: if we have two p-local fusion systems, then the classifying spaces are homotopy equivalent if and only if these triples are isomorphic. So, of course, this is something that we would like to happen. And also, we have the same derived limits results. So, another theorem. So, let F be a saturated fusion system over S. Now, when one has a saturated fusion system, now you have to realize now that we are in the abstract context. The week before, we constructed the central linking system directly from the group. Now we don't have the group. How do we construct the linking system? Well, one has to show that it exists, right? And at the beginning, people didn't know that it existed. Now we know. But what they knew is that there exists a central linking system L associated to F if and only if an element in the limits, in the third limit over the orbit category of the center functor vanishes. So here the orbit category is again the same thing. We have the morphisms in this category, and we quotient by the action of R. Okay? And we also have a result about the uniqueness of these central linking systems. Now, there is a unique L if and only if an element of the derived limits vanishes. Okay. So kind of similar as before. I mean, before we had that if we have an isomorphism between two fusion systems, then we can consider them to be the same. Then we could lift that isomorphism to the linking system if and only if an element of here vanishes. And of course, the reason for that is because if this element vanishes, then there's only a unique central linking system. So the isomorphism is going to lift. Again, I know that I'm not giving many details about them. I don't want to stop. I just want you to know that there exist such things. Huh?
Say a few words about what this element is.
Well, the reason why this element comes is from the fact that we have a projection from L to F, right? And really, this projection is quotient by C in the morphism. So that's the idea of why this element is showing up. So the construction is not that simple, but this is the idea why that element is showing, because of this quotient by the center. Yes, Philip.
Did we define the category of F, or is it similar enough to the definition with G that it doesn't?
Yes. Yeah, well, I just said it by word, but I mean, it will be enough. The morphisms will be these quotients. So the objects are the same, but yeah. So anyway, at this point, like Liang asked, it'd be a good point to wonder, well, are there any examples of this that do not come from finite groups? Because otherwise, what's the point of making all this fuss? So let me talk a little bit about exotic fusion systems. So we say that, exotic p-local finite groups Okay, so exotic p-local finite groups are not p-local finite groups that come from an exotic country. They are just triples that do not come from a finite group, right? We know that there was, so are there others? So this is sort of the motivation for this abstraction. There was already an example in the literature that was kind of exotic, but people didn't know what to do with it. So it all started with a work of Solomon, 74. So Solomon was inside the classification of finite simple groups, right? One of the steps of the classification. So one of the steps of the classification consists in studying the Conway group. So he wanted to classify all finite simple groups that had the same 2-zero subgroup with the same 2-zero subgroup as the Conway group. Now, please don't ask me to say what the Conway group is because I don't know, but it's a group that has an importance in the classification. So in this process, I mean, here eventually he showed that it was only the Conway group. But the way he proved it is the following line of thought. He said, well, if a simple group had the same 2-zero as CO3, then its fusion system will have to be in the following way, trying to get to a contradiction, right? I mean, the conjugations between the subgroups will have to be in this way. Then he didn't find any contradiction. I said, oh, that's strange. Then he said, well, let's try to see how the 2 fusion will relate to the 3 fusion to the 5 fusion. And then he got the contradiction, right? So it turns out that at the prime 2, there was no contradiction. The fusion system was perfectly defined. And, I mean, it defined a fusion system just like we did. But it was only like putting it together with other primes that the contradiction arose. So this was already a fusion system when we still didn't have this definition. Then somebody read this paper and said, well, this is close enough to a finite group that we should be able to associate a classifying space to it. And Benson did that. So Dave Benson, in 98, finished the construction of the 2 local finite group. So constructed a 2 local finite group with this fusion. Now the construction is quite long. Just let me say this. And at this time, we still didn't have a definition of P-local finite group. So it was just like an abstract construction of a space that should be associated to that space in a way. Then, Levy and Oliver, 2002, and at this time, more or less, people had the idea of what a P-local finite group should be. Constructed more examples, sort of generalizations of these ones. Constructed more examples. Generalizing this latter one. Again, the construction is complicated, but let me just say what they did is once you have the zero subgroup, you only need to identify what the centric subgroup should be and what the automorphisms group should be, because it's generated by that. So they kind of made that by hand, and it was quite abstract. And then, more examples that came, and Diaz, Reed, and Viruel, in 2007, studied, well, actually classified all possible P-local finite groups over P groups of rank 2. Now, what does that rank 2 mean? Rank 2 means that the maximal elementary abelian subgroup is CP plus CP.
What does elementary mean?
Well, elementary abelian means precisely this. It's something of the form CP to the n.
Oh,
It's an elementary abelian P subgroup. Yes, maybe I should say here P subgroup. So the maximal n for which we can have a subgroup is called sometimes the P rank.
yeah, okay.
Okay? And of course, many of them were not exotic, but they found some exotic ones. So they found exotic ones for P equals to 3 and P equal to 7. A lot of group theory came into this, a lot of getting into groups. I mean, more groups than topology go into some of these papers, especially in this one.
What sort of group would be associated to the case of these exotic examples?
Well, for the case of these exotic examples, there is no group. Oh, you mean the P-silo? I wouldn't be able to tell you right now, but I can check it out and tell you later. Yeah.
But they would not be elementary, I guess.
No. No, I mean the peer groups of rank 2, they are classified. There is a classification that is kind of nice, and you can go one by one and check it. So they just went one by one and checked all the possible fusion systems and central linking systems that could be constructed. And for some of them, they turned out to be exotic. For some of them, it turned out to be not. But I don't remember right now and which group it will be. But
And the other question would be that this classification is given in terms of what? There is a sort of parameter saying, okay, these two finite p-local groups are same if and only if.
oh, yeah. So in the sense of the isomorphism that I gave you yesterday before.
Sure.
So the
Okay.
yeah. So when are two triples isomorphic?
Yeah. So okay. Yeah.
Any more questions? Now let me just say that we do not have many exotic examples. As you can see, these are almost all of them. There's still one more. And of course, we want to have more, but the construction is, in general, they are hard, and they are not very well understood. I mean, some of them, they are ad hoc constructions, and we would like to understand more about it. But there is one construction that is very interesting. It's kind of going to motivate my passing through to the compact Lie group case, which is the following. So there are other examples, and this is really what one gets an intuition. So Brotto and Moller, 2007, also constructed a whole bunch of exotic p-local finite groups. So they found exotic p-local finite groups as homotopy fixed points of p-compact groups. Now, this is something that I haven't talked about yet. But remember that at the beginning of my talks, I promised that I was going to spend 2 hours on finite case and 2 hours on compact Lie group case. So p-local finite groups are sort of generalizations, in some sense, of finite groups, right? P-compact groups are also, in some sense, generalizations of compact Lie groups, right? Now, if you have ever seen just a few words about the classification of finite simple groups, you would have seen that there are some infinite families, and then there are some sporadic finite simple groups. So the infinite families are the cyclic groups, right? And also some groups of Lie type. Anybody hear about groups of Lie type? More or less? So let's say that, for instance, you can talk about the general linear group, order n, associated to the complex numbers, right? This is a Lie group, not compact, but has compact versions. But one could also talk about the general linear group over finite fields, for instance, this one. And these finite groups are important in the classification of finite simple groups. Some of them, not for GLM, but maybe for constructions as SPN, all these other constructions, some of them turn out to be simple. And the relationship between the compact group and the finite group is sort of like this, through homotopy fixed points. Right? Of course, I will need to talk now a bit about homotopy fixed points, compact Lie groups, and how they are related. So let me now stop talking about finite groups and talk about compact Lie groups. And let me just say that here we found exotic P local finite groups for every P, for every prime. So okay, so compact Lie groups. I spend more time than I should on finite case, but anyway. Okay, so my motivation for studying compact Lie groups and for studying the P-local homotopy theory of compact Lie groups is actually quite different from the one for finite groups. So actually the motivation comes from the classification of compact Lie groups. We all know the classification. So classification, every simply connected compact Lie group is isomorphic to a finite product of simple groups. And in fact, this product, this decomposition is unique up to permutation of factors. Okay. Well, I guess I haven't said what a compact Lie group is, but I guess most people know what a compact Lie group is. Lie group is a group that is also a differentiable manifold. And, well, the multiplication is differentiable, the inverse is differentiable, all that. And compact, well, it's compact. Nothing to explain there. Okay, so this is the classification. And in the classification, moreover, we can specify the list of simple groups. So simple groups are given by 3 infinite families. So SUN, SPN, spin n, and then we have a few sporadic ones. So we have G2, F4, E6, E7, E8. Also, let me just say that these infinite families, some of them they are not simple for some values of n. So you need to specify n bigger than something. I think for spin you need n bigger than 4, because spin 3 is not simple. But let me just say that there are some restrictions here. Okay? Now, if you've ever seen this classification, there is another way to state it in terms of root systems, root data. So another way, well, or maybe I should say the way in which this theorem is proved is by studying some root decompositions of certain vector spaces and classifying this root decomposition. So the way this is proved is by showing that there is a bijection between the isomorphism classes, simply connected compound D groups up to isomorphism and root data over Z. Okay? I'm not going to redefine what root data is, but I just wanted to explain where this combinatorial information is coming from. Okay? So this is up to isomorphism of groups, and this is up to isomorphism of root data that can also be defined. So the way this combinatorial information is coming, it really comes from the maximal torus. And we all know that some of the important information for compound Lie groups is from the fact that they have a maximal torus. Every compound Lie group, G, has a maximal torus T. G is just a product of circles, say n factors, okay? And the group G has an action on T. Well, not the whole group G, but we can look at the normalizer of the torus in G. That is the elements of G that normalize T. Yeah? This group has an action on T, just by conjugation. That's clear, right? Also, T is abelian, right? Now, inside the normalizer, we can see they also have T, but the action of T by conjugation of T is trivial, because the group is abelian. So this action also gives me an action of the Baer group, which is this quotient. This is the Baer group. Gives me an action of this on the torus. Right? So actually, this combinatorial information is coming from this action. How? Well, the action of the Baer group on the torus induces an action of the Baer group on the fundamental group of the torus. So we get an action of this group on pi 1 of the torus. And we do know that this is C to the n. Yep. And this is an action through group automorphisms. So we can also think of that as a map from this group into the group automorphisms of Cn. And this is usually denoted by GLN of C. Okay? Now, funny thing here, the automorphisms of Zn and the automorphisms of T, just as a group, they are the same thing. How? Well, we have a bijection given as follows. If we have an automorphism of T, we can take the morphism induced in the fundamental group, taking pi 1, goes up. And for the inverse, we can take the map induced in the by taking classifying spaces. And these are inverses of each other. So this is actually a bijection. Yeah. Now, from here, we can actually get something else. If we look at this map, and we think of this as the automorphisms of T, what is the kernel of this map? Where they are the elements of NGT, right, that fix every point of T. Right? That will go to the identity. Yeah? And well, and quotient by T, because we are in the fine group. So the kernel, say F, will be CGT, the centralizer, quotient by T. Yeah? But if you have ever seen how we find the maximal torus, we realize that the maximal torus is self-centralized. So this is actually the trivial group. So this is an injection. In fact, we have the WT is a subgroup of G, L, and Z. Yeah? Well, we get something interesting from here that is not completely obvious. This is a discrete group. So this also has to be a discrete group. With a bit more effort, one can actually show that this is finite, in fact. Yeah? And this is actually something very interesting to study. What are the finite subgroups of these kind of subgroups, which are discrete? We also have an induced map. If we tensor with Q, for one tensor with Q, things become simpler. So we also have an induced map in G, L, N of Q. It's also an inclusion. And in this case, not only this is finite, but if we look at the image here, the image is generated by reflections. And what do I mean by a reflection? Well, a reflection is a non-trivial element that fixes a subspace of codimension 1. So i.e., non-trivial elements that fix a codimension 1 subspace of Qn. Okay, why am I going so much about this? Well, this actually is the definition of a reflection group. So we say that WGT is a Q reflection group. Okay, so it's a finite subgroup of this, which is generated by reflections. Yeah. So what is this root data over Z? This root data over Z is just the information that we need, or the way to classify all the Q reflection groups. So the way the proof will go is anytime you have a Q reflection group, you get some sort of root data. From the root data, you get these, how's it called? The Dinkin diagrams and these graphs. And then you can classify all these graphs. And that's how the classification works. So, yes?
Here is the prediction with the root data. You need the simply assumption. If you could connect the compactly group, you also have this maximal torus and
Well, it depends on what you mean by root data. The way that we classically see root systems, you do need the simply connected. Yeah. But there are ways to improve the information that is here so that we can also just leave here connected.
it is possible.
It is possible with putting some more information here. So there are something called root systems. And these ones are in a correspondence with simply connected compactly group. There is something a bit more general, which is called root data. And for this one, classifies all connected compactly groups.
But it's root data over C again.
It's still root data over C, yeah. I just didn't want to get into these details because they are, but yeah. Yeah. Okay, more questions about this? So anyway, what I'm trying to demonstrate with all this is that most of the important information about a compactly group comes from the action of the Biot group on the torus. So if one wanted to generalize that, this should be an element that will be in the generalization. Right? Now, of course, here we are in a topology conference. So this is also motivated by results in homotopy theory. So the generalization because once people have the classification of compactly groups, proving theorems about compactly groups was a matter of going through the classification and checking case by case. So in the 30s, 40s, and 50s, there were a lot of results in homotopy theory of compactly groups just by checking, right? So let me talk a bit about the homotopy theory, compactly groups. So I'm going to assume that I have a group that is simple, a GB simple, just so that the results are stated more simply. So I want to talk about first a couple of results that are interesting. One is what is the cohomology of G with coefficients in Q. Yeah. So this turns out to be isomorphic to an exterior algebra on a certain number of odd dimensional generators. Well, 2n plus 1. They don't have to be consecutive, but they have to be odd dimensional, all of them. And it has to start from 3, from degree 3. But the interesting thing about this is that if I count how many generators are in here, that coincides with the rank of G. So the number of generators gives me the rank of G, the dimension of the maximal torus. Which is interesting because from this homological information, you get this kind of geometric information about the group. Yeah. So the next result is also in the same vein.
Can you repeat dimensions?
For simple, I think you cannot repeat. Now in the generalization you can, but yeah, in general, no. For compactly groups they don't repeat. Yeah.
Increasing sequence.
Yeah, it's an increasing sequence, yes. If it wasn't simple, then you could repeat, because you could have two x3s. It's just two copies of the same thing. Yeah. Now, the other result that's interesting is when we look at the cohomology with coefficients in C of G over T. So T is the maximal torus, okay? So the homogeneous space. Well, this turns out to be torsion-free. And concentrated in even dimensions. Okay. In fact, people gave us cellular decomposition of these spaces, G over T. But maybe, how much time do you have? Okay. But for me, what's more interesting about this, since this is torsion-free, the cohomology is just a sum of many copies of C. Yep. So if one looks at the rank over Z of this, this is equal to the size of the Weil group. Okay, these are really surprising. Now, I mean, from these two results and others, people started getting the idea that maybe one should be able to characterize compactly groups in terms of the homotopy. That there should be a description like X is homotopy equivalent to a compactly group if and only if something happens in terms of homotopy. So the question that drove this generalization was precisely that question. Can we characterize compactly groups from the point of view of homotopy theory? And it turns out the answer is yes, we can. But the answer, even though the answer is simple, it took a long time to be proved. So let me give you the answer. So theorem, and this was originally called the maximal torus conjecture. So the theorem says that X is homotopy equivalent to a compact D group if and only if it is a finite loop space with a maximal torus.
You said finite loop space.
Right. So now I have to define a few things. So what do I mean by loop space? What do I mean by finite? Finite is not the finite number of points. And what do I mean by maximal torus too? Because I mean, we know what a maximal torus means for a compactly group. But for a loop space, this definition is something more homotopic. Okay? So what I want to do next, I think I have time to talk about this a bit, is to explain the terms of this theorem, what it means. And let me say also that this theorem was not proven until 2008, 2009. So it's quite recent. So to explain this, I want to talk a bit about H spaces and loop spaces.
In this theorem, you're supposed to assume that X is simply connected.
No, I'm not. I think no. I think I'm assuming that it's connected only. Connected, yes. But I mean, most of what I'm going to talk, I'm going to assume that all my spaces are simply connected, because then the arguments for connected is just going to covering spaces. But yeah, I mean, the important arguments are for the simply connected case. Okay, so let me talk just a bit about H spaces. So when one looks at generalizing compactly groups from the point of homotopy theory, one say, well, instead of having a product, I want to have a product up to homotopy, right? So this is just an H space. So one thing that was clear from the beginning is that compactly groups are H spaces. But moreover, I'm not making justice here with the compact part. So how does the compact part translate into the homotopic world? Well, when we have a compact manifold is homotopy equivalent to a finite CW complex. So that's what I mean by finite. So they are actually finite H spaces, where finite means homotopy equivalent to a finite CW complex. Okay? And when one studies the homotopy theory of H spaces, one already gets this result already. Right? Well, when we have an H space, in the cohomology we have a multiplication, but we also have a co-multiplication, yeah, induced by the multiplication in the H space. So the cohomology of an H space is a Hopf algebra. So if X is an H space, then the cohomology, and let's say with coefficients in Q because that's what I'm interested, is a Hopf algebra. Sorry? Is there a co-unit? Yes, let me see. Co-unit. Do we have a co-unit? So we have a unit. Yeah, because you have the point getting into X.
Okay, so X is.
So you get, yeah.
Okay.
That induces the co-unit, yes. Okay, so maybe I won't have time to explain that. I will continue next time, but but where does that form come? This comes from the fact that finite dimensional of algebras are classified. And when I talk about Hopf algebras, I'm always talking about graded like in cohomology, graded, commutative, all that. So finite dimensional Hopf algebras are classified, and they all have this form, except for they don't have to start with X3, but they have to be of the form exterior algebras on odd dimensional generators. Yeah. On a finite number of odd dimensional generators. And this number, n, the number of generators, again has an importance for the study of H spaces, so it has a name. N is called the rational rank of X. Well, I'm running out of time. In fact, I'm already over the time. So I'm going to stop here. But let me just say that compactly groups are more than H spaces. They're actually loop spaces, right? So what I'm going to talk about next is how compactly groups are loop spaces and what it means for a loop space to have a maximal torus. But for an H space, it doesn't make sense to talk about that, but for loop spaces, it will. So, okay. So I stop.